The farthest human beings have ever travelled is still the Moon, only about 250,000 miles from Earth. Beyond that record lies Mars, the outer planets, the heliopause, and finally Proxima Centauri, more than 4 light-years away. The question is not just how powerful a rocket can be, but how long a human body can survive radiation, isolation, weightlessness, and the enormous patience of deep space. If calm, thoughtful science journeys like this are worth returning to, a gentle like, subscribe, or share helps this channel keep creating them. Thank you for spending part of your time here. Leave a comment with where you're watching or listening from, and what time it is there, whether this is a late-night listen, a study companion, or a quiet moment before sleep. The path outward begins with the record we already hold, and the much larger distances still waiting beyond it. The most useful place to begin is not at the edge of the galaxy, or even at the edge of the solar system. It is the Moon, because the Moon remains the farthest place any human body has ever reached in 2026, after more than half a century of robotic exploration, orbital observatories, planetary probes, and images from worlds no person has seen directly. The human distance record is still set by the Apollo missions. 12 people walked on the lunar surface between 1969 and 1972. The greatest distance from Earth reached by any crew was roughly 250,000 miles, depending on the exact position of the Moon and the mission path. That is far by every ordinary human measure. It is far enough for Earth to become a small world in a black sky. It is far enough for radio signals to need more than a second to cross the distance each way. It is far enough to make the return home depend on engines, guidance, life support, thermal control, and careful navigation working together without rescue. Yet in astronomical terms, it is almost nothing. The Moon is close enough that Earth still dominates the sky, close enough that its gravity remains the central fact of the journey, close enough that a mission can leave, land, and return in days. This first fact is uncomfortable because it makes the question sharper. Human beings have not yet become a deep space species. They have briefly visited the nearest large body beyond Earth, and then stopped. Robotic machines continued outward. Voyager 1 passed the heliopause and entered interstellar space. New Horizons crossed the Pluto system and kept moving into the Kuiper belt. Orbiters have studied Mars, Jupiter, Saturn, Mercury, Venus, and small worlds between them. But a machine reaching a place is not the same as a person living through the journey. A camera does not need bone density. A radio transmitter does not need sleep, social stability, protection from cancer, or confidence that its children will inherit the purpose of the mission. The question of how far humans could travel is therefore not just a question about distance. It is a question about bodies, engines, time, energy, and meaning. The distance to Mars begins to show the difference. Mars is the near doorway for human exploration beyond the Moon, not because it is easy, but because it is the first destination where the whole problem becomes clear. At closest approach, Mars can be about 34 million miles from Earth. At other times it is much farther, because both planets are moving around the Sun on separate orbits. A chemical rocket cannot simply aim at where Mars appears and fly in a straight line. It has to depart during a favourable window, enter an orbit around the Sun that intersects the orbit of Mars, and arrive when Mars is there. With present chemical propulsion, the one-way trip is commonly measured in months. That is already a different human challenge from Apollo. A lunar crew lived for days beyond Earth. A Mars crew would live for many months in deep space, then possibly for months or years on another planet, then wait for the orbital geometry that allows a return. The distance is only the visible part of the difficulty. During the transit, the crew would be outside Earth's magnetic field for much of the journey. exposed to solar particle events and galactic cosmic rays. In weightlessness, bones lose mineral density, muscles weaken, fluids shift toward the head, and the cardiovascular system adapts to a condition the human body did not evolve to occupy. Inside the spacecraft, air, water, food, waste processing, temperature, pressure, medical support, and social order all have to be maintained with no nearby harbour. Mars is not beyond known physics. It does not require a new theory of nature. It requires engineering discipline, biological countermeasures, radiation planning, surface systems, and political commitment strong enough to sustain the work. That distinction matters. The first ceiling is not the law of the universe. It is the practical ceiling of current civilization. The gap between the Moon and Mars is already large, but it is still only the beginning of the larger scale problem. The Moon is about 250,000 miles away. Mars at a favourable approach is more than 100 times farther. Jupiter is hundreds of millions of miles from the Sun. Saturn is farther still. Neptune is nearly 3 billion miles from the Sun, and even that is not the outer edge of the Sun's influence. The heliopause, where the solar wind gives way to the interstellar medium, lies far beyond the planets. None of these distances are intuitive. They do not fit easily inside the human sense of travel, because human travel evolved around landscapes, rivers, mountains, roads, and oceans. Space travel is governed by orbital mechanics and propulsion limits, radiation, and life support duration. A journey outward is a long negotiation with motion itself. A ship must not only cover distance, it must change velocity. It must leave one gravitational environment, enter another, and often slow down at the destination. It must carry the systems that keep human tissue alive while every extra kilogram makes propulsion harder. This is why the answer cannot be one simple number. How far humans could travel depends on what kind of travel is being described. A flyby is one answer. A spacecraft can pass a target at high speed, collect data, and continue onward. A robotic probe can do this well. A human flyby is possible in principle, but it is a strange form of presence, because the crew would spend years travelling for only a brief encounter. An orbital mission is another answer. To orbit another world or another star, the ship must arrive with enough ability to slow down and be captured. A landing is a deeper answer still, because the crew must descend, survive on the surface, and possibly ascend again. A return mission is the hardest common version, because the journey must be solved in both directions. Each layer adds mass, time, risk, and energy. The same destination can be easy for a flyby and nearly impossible for a landing and return. The Moon is the only place beyond Earth where humans have completed the full chain. They travelled, landed, worked, lifted off, rendezvoused, and came home. That achievement remains extraordinary because it was complete. It was not only arrival, it was return. The next useful separation is between what current technology can do, what known physics allows, and what future civilization might choose to build. These are often blended together in casual discussion, but they are very different boundaries. Current technology places human beings near Earth, and, with enough development, plausibly on Mars. Known physics allows much more. No known law prevents a spacecraft from travelling to the outer solar system with people aboard if propulsion, shielding, power, life support, and mission architecture are solved. No known law prevents a ship from crossing to another star at a fraction of light speed. The universe does not forbid such a journey. It simply makes it expensive in energy, slow in human terms, and severe in biological consequences. Civilizational choice is the third boundary. A society may understand how to build something and still decline to build it. The Apollo program ended after a few years of lunar landings. Nuclear thermal propulsion was tested on the ground and then cancelled. Nuclear pulse propulsion was seriously studied and then made politically and legally unacceptable because of the risks attached to nuclear detonations. The history of human space travel is therefore not a smooth curve outward. It is a record of capability rising, pausing, shrinking, and rebuilding. The physical map is not the same as the political map. That is why the moon remains such a powerful baseline. It is not only a nearby world, it is a reminder that human reach is controlled by more than ambition. A person can travel only as far as the supporting system can carry them. That system includes engines, propellant, shielding, food production, recycling, navigation, communication, medicine, governance, funding, and patience. Remove one of them, and distance stops being a number on a chart and becomes a hard limit. Add a better engine, and the map changes. Add stronger radiation protection, and the map changes again. Add reliable artificial gravity, or biological resistance to radiation, or suspended animation, and the map changes in a different way. The ceiling is not a single roof. It is a stack of ceilings, each one made from a different constraint. The lowest ceiling is where humans have already been. The next is where current engineering can plausibly go. Beyond that are the places that known physics permits but present systems cannot yet support. Farther still are the destinations that require not only technology, but a civilization willing to think in decades, centuries, or longer. The central question therefore becomes more precise. It is not simply how far a human could travel into space, it is how far a living human society can push engines, bodies, institutions, and purpose before one of them fails. From that view, the moon is not the answer. It is the first measured point on a much longer scale, and the distance beyond it is shaped by limits that are physical, biological, and human at the same time. A chemical rocket is a machine built around a simple exchange. It throws mass backward so the vehicle moves forward. The force may look overwhelming at launch, with engines shaking the ground and flames spreading beneath the vehicle. But the underlying rule is quiet and exact. Momentum has to be conserved. A rocket carries propellant, accelerates that propellant out of its engines, and gains motion in the opposite direction. This is why rockets work in the vacuum of space. They do not push against air. They push against the mass they carry and expel. In a chemical rocket, the energy that drives this process comes from chemical bonds. Fuel and oxidizer react inside a combustion chamber, producing hot gas. That gas expands through a nozzle and leaves the engine at high speed. The higher the speed of the exhaust, and the more efficiently the engine uses its propellant, the more change in velocity the spacecraft can achieve. For human spaceflight so far, this method has been enough. It placed Yuri Gagarin in orbit. It sent Apollo crews to the moon. It carries crews to low Earth orbit. It can launch the pieces of a Mars mission and send a crew outward if the mission is carefully designed. Chemical propulsion is not primitive. It is mature, powerful, and dependable by the standards of present engineering. Its limitation is not that it fails to work. Its limitation is that it works within a narrow energy range set by chemistry itself. The fuel can be refined, the engines can be improved, and the tanks can be made lighter, but the energy released by burning hydrogen, methane, or kerosene with oxygen cannot be made arbitrarily larger. Nature fixes the energy stored in those bonds. Once an engine approaches the best possible performance for that reaction, the remaining gains become small. This is the chemical wall. It is not a wall that appears at launch, because launch is exactly where chemical rockets are strongest. Their high thrust is well suited to climbing out of Earth's gravity. The wall appears when the mission has already left Earth. and distance begins to demand more velocity than chemistry can provide without impossible amounts of propellant. The Moon sits within the range of this technology because the journey is short enough and the required velocity changes are manageable. Apollo used a large launch vehicle, staged away empty hardware, entered lunar orbit, landed a small module, and returned a smaller crew cabin to Earth. The whole mission architecture was shaped around the fact that propellant is heavy and empty mass is costly. Mars can also be placed within the chemical range, but only by accepting long transit times and narrow launch windows. A typical chemical mission to Mars does not fly directly in the everyday sense. It follows an efficient solar orbit that intersects Mars months later. This saves propellant, but it makes the crew spend a long time between planets. A faster chemical route is possible in principle, but it requires much more propellant, and the mass of that propellant must also be launched, accelerated, stored, and managed. The trade becomes severe very quickly. This is why Mars is not simply the Moon at greater distance. Mars takes the same basic propulsion method and stretches it until the other systems begin to carry much of the risk. Radiation exposure accumulates during the cruise. Microgravity effects deepen over time. Food, water, maintenance, spare parts, and medical support become harder to guarantee. A chemical rocket can provide the initial push, but it does not remove the months that biology has to endure. The problem becomes clearer beyond Mars. Jupiter is not just farther away. It is embedded in a mission environment where travel time, radiation, and braking demands become much more difficult. A chemically propelled crewed mission to the Jovian system would need years, not months, unless it carried an enormous amount of propellant. The destination itself is also harsh. Jupiter has intense radiation belts, and any mission to Europa, Ganymede, or Callisto would have to manage both arrival energy and environmental danger. Saturn is farther still. Uranus and Neptune move the problem into timescales that are poorly matched to present human spaceflight. Robotic spacecraft can survive long coasting journeys because they are built for low-power operation and do not need to protect living tissue. Cassini could spend years travelling to Saturn. New Horizons could cross to Pluto on a fast but still long robotic trajectory. A crew cannot be treated the same way. A person is not only payload. A person brings a whole living system around them. The ship must hold pressure, remove carbon dioxide, recycle water, control temperature, protect against radiation, provide food, manage waste, support exercise, monitor illness, and keep the crew psychologically functional. Every protective layer adds mass. Every kilogram of mass demands propulsion. Chemical propulsion can support this burden for near destinations. It becomes increasingly unsuitable as the distance grows. One reason this limit is easy to underestimate is that rocket launches look as if they contain almost unlimited power. A large chemical launch vehicle releases energy at an enormous rate. The first minutes of flight are among the most intense events humans can engineer. But power at launch is not the same as efficient deep space travel. The vehicle burns through most of its propellant simply to reach orbit. Earth orbit is already a major achievement because Earth's gravity is deep and its atmosphere adds drag and heating. After orbit is reached, any mission beyond Earth needs additional velocity changes. It must depart Earth, adjust its path, possibly enter orbit around another body, possibly land, and possibly return. Each of these steps draws from the same limited propellant budget. Staging helps because empty tanks and engines can be discarded. Gravity assists help because a spacecraft can exchange a small amount of momentum with a planet and reshape its path. Careful trajectories help because orbital mechanics can reduce the required energy. But none of these methods changes the energy density of the fuel. They're ways of spending the budget wisely, not ways of making the budget unlimited. For a Mars mission, wise spending may be enough. For the outer planets with humans aboard, it is not enough in any comfortable sense. The farther the target, the more the mission is forced to choose between speed and mass. A slow route saves propellant but exposes the crew for longer. A fast route reduces time but requires far more energy. Chemical rockets sit in a difficult middle. They're powerful enough to begin the journey and not efficient enough to shorten it radically once the destination is far away. This is why the chemical ceiling is best understood as a practical boundary rather than an absolute one. A chemical rocket could send a human spacecraft onto a long path into the outer solar system if enough hardware were assembled and the mission accepted extreme duration and risk. The question is not whether an engine can point outward. The question is whether the whole mission remains humanly survivable, operationally sensible, and scientifically worth the cost. Under that standard, chemical propulsion reaches its meaningful limit around Mars. It can help open the inner solar system. It cannot make the solar system feel small. The same issue becomes decisive when stars enter the discussion. The nearest star system lies more than 4 light-years away. At the speeds reached by present spacecraft, the crossing would take many tens of thousands of years. A chemical rocket does not merely perform poorly in that setting, it stops being a plausible interstellar propulsion system at all. The reason is, again, energy density and exhaust velocity. To accelerate a spacecraft to even a small fraction of light speed, a chemical rocket would require propellant masses that grow beyond practical or planetary scale. The spacecraft would need fuel to accelerate the fuel that accelerates more fuel, and the mass problem would compound beyond usefulness. This is not a failure of imagination. It is the result of the rocket equation, which appears in the next step of the argument. For now, the important point is that chemical rockets define the first real map of human travel. On that map, Earth orbit is routine by comparison with the rest. The Moon is proven. Mars is difficult but physically reachable, and the outer solar system remains outside practical crewed access. Chemical propulsion is therefore both the foundation and the constraint. It gives humanity the first step away from Earth, but it also shows why leaving Earth is not the same as becoming capable of deep space travel. The engines that made the space age possible are not the engines that can carry human beings across the full scale of space. They are the beginning of the ladder, not the top of it. The rocket equation is not dramatic, but it is one of the most important limits in the history of spaceflight. It describes how much a rocket can change its velocity, based on the speed of the exhaust leaving the engine and the ratio between the vehicle's full mass and its empty mass. That relationship was worked out by Konstantin Tsiolkovsky in the late 19th century, before any machine had reached space. Its importance comes from a simple fact that is easy to state and difficult to escape. A rocket must carry the propellant it later uses to move. At the start of a burn, the engine is not only accelerating the spacecraft and its payload, it is also accelerating the unused propellant still inside the tanks. More propellant can provide more future thrust, but it also makes the vehicle heavier right now. That extra weight requires more propellant to accelerate, and that additional propellant also has mass. This is the loop that makes rocket design unforgiving. It's not enough to say that a spacecraft needs more fuel. The fuel becomes part of the problem it's meant to solve. The rocket equation gives this problem a precise shape. It shows why small improvements in engine efficiency can matter greatly, and why low efficiency becomes fatal when the goal is very high speed. The key variable is exhaust velocity, the speed at which propellant leaves the engine. If the exhaust leaves slowly, each kilogram of propellant provides only a limited change in the spacecraft's motion. If the exhaust leaves very quickly, the same kilogram can do more. Chemical rockets have high thrust, which makes them useful for launch and major maneuvers. But their exhaust velocity is limited by the energy released in chemical reactions. That is why they can lift massive vehicles from Earth while still being poor tools for interstellar travel. Thrust and efficiency are related, but they are not the same thing. A launch vehicle needs enormous thrust because it must rise against gravity and pass through the atmosphere. A deep space vehicle needs efficient velocity change over time. It may not need to push hard at every moment, but it needs to spend propellant in a way that produces large total changes in speed. This distinction explains why different propulsion systems can have very different roles. A chemical engine can produce huge force for minutes. An ion engine can produce a tiny force for months or years. The ion engine may be far more efficient, but its low thrust makes it poorly suited for rapidly moving a crew out of danger or shortening a human journey by a large amount unless power is also increased greatly. The rocket equation does not choose the mission. It tells the mission what the cost of each choice will be. For short journeys, the cost can be managed. For longer journeys, the cost begins to dominate everything else. To reach Mars with a chemically propelled architecture, mission planners accept a relatively slow transfer because it reduces the required change in velocity. The crew spends months in transit because the alternative demands much more propellant. To reach the outer planets quickly, the required velocity change rises. To slow down once there, it rises again. If a landing is required, more propellant is needed for descent or ascent. If a return is required, more must be carried or produced. Each demand adds mass, and the mass affects every earlier stage of the mission. This is why distance alone gives an incomplete picture. A destination can be physically near compared with the stars and still be hard to reach with people, because the complete mission architecture becomes heavy. A spacecraft going to Jupiter is not only crossing space, it is carrying the means to keep humans alive, to protect them from radiation, to communicate across large delays, to maneuver near a giant planet, and to avoid arriving so fast that it cannot do useful work. The rocket equation is present in all of those decisions, because all useful hardware has mass. Shielding has mass, water has mass, spare parts have mass, food systems have mass, larger habitats have mass. Artificial gravity systems, if used, would have mass. The more humane and safer the spacecraft becomes, the harder it becomes to accelerate. This is one of the central tensions in crewed deep space travel. Human needs push the mass upward, while propulsion limits push the mass downward. A robotic probe can be small, patient, and lightly shielded. A crewed vessel must be large enough to be survivable. The equation does not care which payload is scientifically valuable or morally important. It treats every kilogram the same. Energy density is the deeper reason one propulsion tier differs from another. Chemical reactions release energy from rearranging electrons in atoms and molecules. Nuclear fission releases energy by splitting heavy atomic nuclei. Fusion releases energy by joining light nuclei under extreme conditions. Antimatter annihilation would release energy by converting mass directly into energy when matter and antimatter meet. These are not merely different engines. They are different levels of stored energy. Higher energy density makes it possible to heat or accelerate propellant to higher speeds. Higher exhaust velocity then allows larger velocity changes without propellant masses becoming unreasonable. This is why the hierarchy of propulsion is also a hierarchy of reach. Chemical propulsion can begin the space age, but it cannot carry large human missions to the stars. Nuclear thermal propulsion can improve the Mars problem, because it heats a light propellant such as hydrogen more efficiently than chemical combustion can. Ion propulsion can move robotic spacecraft with impressive economy, because charged particles can be accelerated to very high speeds, though the thrust is small. Nuclear pulse propulsion, if allowed and engineered safely, would use nuclear explosions to deliver repeated impulses with far higher energy than chemical rockets. Fusion propulsion would move the energy source closer to the power of stars. Antimatter would be near the upper limit of known rocket energy, though its practical problems are severe. The rocket equation explains why these steps are not small refinements. Each one changes the relationship between useful payload and required propellant. When exhaust velocity increases, missions that once required impossible mass can become possible mass. That does not make them easy. It makes them no longer ruled out by arithmetic. This is especially clear when interstellar travel is considered. The nearest star is not just farther than Mars by a large amount. It is separated by a scale where ordinary planetary travel comparisons stop being useful. At current spacecraft speeds, a crossing to the nearest star would last tens of thousands of years. To reduce that journey to decades, a ship must travel at a significant fraction of light speed. That requires an immense change in velocity. With chemical exhaust velocities, the propellant requirement grows beyond any practical meaning. The vehicle would need such a vast quantity of fuel that the mission would cease to resemble an engineered spacecraft. It would become a mass problem larger than the payload, larger than the infrastructure, and eventually larger than anything civilization could assemble for the purpose. The equation is not saying that the nearest star is unreachable in all possible futures. It is saying that chemical propulsion is not the method. A different energy regime is required. The same logic applies, in milder form, across the solar system. The outer planets are not forbidden. They are blocked by the combination of travel time, human survival needs, and propellant efficiency. A high-energy propulsion system would not move the planets closer, but it would change the time and mass required to reach them. That is what redrawing the map really means. It means a destination shifts from theoretically possible, but impractical, to operationally plausible. The solar system contains many such thresholds. Mars is near the edge of chemical practicality for crewed missions. Jupiter and Saturn become more realistic only when propulsion improves enough to reduce travel time and arrival difficulty. The Kuiper Belt and the heliopause require still greater capability if humans are to go there with any serious chance of returning or continuing useful work. The stars require another category entirely. The rocket equation also reveals why there is no single answer to how far humans could travel. The answer changes with exhaust velocity, power supply, vehicle mass, mission duration, and whether the crew must stop, land, or return. A small probe, a crude flyby ship, a generation vessel, and a return mission are not the same problem. They obey the same physics, but their masses and requirements are different enough that each belongs to a different distance ceiling. This is why the next propulsion tiers matter so much. They are not optional upgrades to the same journey. They are the conditions under which new journeys become possible at all. The equation does not discourage exploration, it clarifies it. It shows that the route outward is not opened mainly by desire, but by exhaust velocity, energy density, mass discipline, and careful mission design. Once those terms are understood, the distance question becomes less vague and more exact. The first barrier is chemistry. The next barriers are nuclear energy, fusion control, antimatter handling, and the biological mass required to carry human life through space. The rocket equation sits beneath all of them, quietly deciding how much of the universe can be reached by a ship that must carry its own means of motion. Between the force of chemical rockets and the more difficult possibilities of fusion and nuclear pulse propulsion, two technologies occupy an important middle ground. One is already proven in space, though mostly for machines rather than people. The other was proven on the ground decades ago and is now being prepared for a new attempt in flight. They are ion propulsion and nuclear thermal propulsion, and they are often discussed as if they belong to the same future. In practice, they solve different parts of the travel problem. Ion propulsion is a lesson in patience and efficiency. Nuclear thermal propulsion is a lesson in faster crewed movement within the inner solar system. Neither one makes the nearest stars reachable. Neither one turns Neptune into a casual destination for human crews, but both show how the map begins to shift once propulsion stops depending only on combustion. Ion propulsion works by giving an electric charge to a propellant, commonly xenon, and then accelerating those charged particles through electric fields. The exhaust leaves at much higher speed than the exhaust from a chemical engine. That means each small amount of propellant can produce more total change in velocity. The engine does not push hard. Its thrust is extremely small, often closer to the weight of a sheet of paper than the force associated with a launch vehicle. But in space, where there is almost no drag, a small push can matter if it continues for months or years. This is why ion propulsion has been so valuable for robotic missions. NASA's Dawn spacecraft used ion engines to visit Vesta, leave orbit there, and then travel onward to Ceres. That sequence was unusual because the spacecraft did not merely fly past its targets. It entered orbit around one body, departed, and later entered orbit around another. A chemical spacecraft of similar mass would have struggled to carry enough propellant for that kind of mission. Ion propulsion made the mission possible by spending propellant slowly and efficiently. Other missions have used related electric propulsion systems for deep space navigation, asteroid missions, and efficient orbital changes. The technology is real, tested, and useful. Its weakness is equally real. A crewed spacecraft is not a small robotic probe. It is a large life support system with engines attached to it. It must move people within time limits set by radiation, health, supplies, and psychology. A very low thrust engine may eventually build up high speed, but it cannot easily provide the kind of rapid departure, braking, or emergency maneuvering that human missions often require. The passengers cannot wait indefinitely while a tiny acceleration slowly accumulates. A robotic spacecraft can accept a long spiral outward from Earth or a slow reshaping of its solar orbit. A human mission has less freedom, because every extra month adds exposure and operational risk. Electric propulsion can still support crewed exploration in indirect ways. It may move cargo ahead of time. It may reposition supplies, habitats, or return propellant before a crew launches. It may help build infrastructure between Earth, the Moon, and Mars. It may reduce the mass that chemical rockets have to push during later crewed missions. In that role, it is valuable. It extends logistics. It does not by itself open the outer solar system to people. The other limitation is power. Ion engines need electricity. Near Earth, large solar arrays can provide useful power. Farther from the Sun, sunlight weakens with distance. At Mars, solar power is still possible but reduced. At Jupiter, it is much weaker. At Saturn and beyond, solar arrays become large and inefficient for major propulsion demands. Nuclear electric power could run ion engines far from the Sun, and that combination has been studied seriously. But then the mass of the reactor, radiators, power conversion equipment, and shielding becomes part of the same mass problem. The propulsion becomes efficient in propellant but heavy in hardware. For robotic spacecraft, this trade may be acceptable. For large crewed ships, it does not create the sharp reduction in travel time needed to make distant targets comfortable. Ion propulsion therefore changes what can be done with small payloads and careful planning. It does not change the human ceiling in the way a higher energy propulsion system would. Nuclear thermal propulsion approaches the problem from a different direction. It still works like a rocket in the basic sense, because propellant leaves a nozzle and the spacecraft moves the other way. The difference is the heat source. Instead of burning fuel with oxygen, a nuclear reactor heats a light propellant, usually hydrogen, to very high temperature. The hot hydrogen then expands through the nozzle and produces thrust, because hydrogen is light. And because the reactor can heat it more effectively than chemical combustion allows, the exhaust velocity can be much higher than that of a chemical rocket. Nuclear thermal engines can have roughly about twice the efficiency of the best chemical engines, while still producing meaningful thrust. That combination matters for crews. It means shorter travel times, larger launch windows, and more flexible trajectories, especially for Mars. This is not a distant concept invented only for speculation. The United States tested nuclear thermal rocket engines during the NERVA program in the 1960s and early 1970s. Those engines were built and fired on the ground. They demonstrated that a reactor could heat hydrogen and produce rocket thrust. The program ended for political and budgetary reasons after the lunar race lost urgency, not because the basic engine concept had failed. That history is important because it places nuclear thermal propulsion in a different category from many advanced ideas. It is not simply a paper design. It is a technology with a tested foundation, left unfinished before it could fly. In the present era, NASA and DARPA have returned to the idea through the Draco program, which aims to demonstrate nuclear thermal propulsion in space. A successful flight test would not instantly create Mars ships, but it would move the technology from ground heritage to space operation. That step would matter because space adds constraints that ground tests cannot fully settle. A flight engine must operate with real thermal loads, real control systems, real start-up and shutdown procedures, and real safety requirements in orbit. Once those are demonstrated, mission design changes. Mars becomes more accessible, not because the planet moves closer, but because the trip can be shortened and the trajectory options can widen. A crew that might spend 6 to 9 months in transit with chemical propulsion could, under some nuclear thermal mission designs, make the crossing in roughly 3 to 4 months. That reduction is not minor. It cuts the time exposed to deep space radiation. It reduces the period of weightlessness. It lowers the amount of food and consumables needed during transit. It may improve abort options and give planners more freedom in choosing departure paths. For human health, time is not a neutral variable. Shortening the trip can be as important as improving the habitat. Still, nuclear thermal propulsion should not be mistaken for a Starship engine. Doubling chemical efficiency is powerful inside the inner solar system, but the outer solar system remains large. Jupiter would still require long mission durations with difficult radiation and arrival demands. Saturn would remain farther than any present human system is prepared to handle. Uranus, Neptune. And the heliopause would still be major expeditions far beyond the comfort zone of current biology and infrastructure. Nuclear thermal propulsion improves the first deep space step. It does not erase the scale of the solar system. Its value lies in making Mars missions more robust and making sustained operations around the Moon and inner planets more practical. It could serve as a bridge technology, a way to learn how to operate nuclear systems in space, how to protect crews and hardware, how to manage higher energy missions, and how to build confidence before attempting more radical propulsion. The difference between ion propulsion and nuclear thermal propulsion therefore reveals a useful pattern. One is efficient but gentle. The other is more forceful but still bounded. Ion propulsion saves propellant over long periods and excels when time is flexible. Nuclear thermal propulsion saves time for large vehicles and becomes especially useful when passengers are aboard. Together, they do not overturn the distance problem, but they refine it. They show that progress is not always a single leap from chemical rockets to interstellar ships. Sometimes it's a series of partial gains that move the practical frontier outward in specific ways. Cargo can go ahead of crews. Mars transfers can become shorter. Nuclear reactors can become part of normal spacecraft engineering. mission planners can gain more room to trade mass, time, and safety. These are not small achievements. They are the conditions under which human exploration becomes less fragile. Yet the underlying map remains recognizable. The moon has been reached. Mars becomes more plausible. The asteroid belt becomes more accessible to machines and perhaps future staging systems. The outer planets still demand another kind of propulsion if people are to go there and return within ordinary human time. Electric and nuclear thermal engines are therefore not the final answer to how far humans can travel. They are the first signs that the answer can change. They lift the ceiling above chemistry, but they do not lift it beyond the solar system. The next real transformation requires an engine that does not merely improve the old map, but makes the whole solar system feel reachable. Project Orion begins with an idea that sounds less like ordinary rocket engineering than almost anything that came before it. Yet it was studied with unusual seriousness. A large spacecraft would carry a supply of nuclear explosive units and release them one by one behind the vehicle. Each detonation would expand into plasma, strike a massive pusher plate, and drive the ship forward. Between the pusher plate and the crude structure, shock absorbers would spread the sharp impulse into a smoother acceleration. The concept did not rely on pushing against air, and it did not require a combustion chamber. It used nuclear energy directly, not to heat a reactor core in a controlled flow, but to create repeated bursts of momentum outside the vehicle. This is nuclear pulse propulsion, and it matters because it is one of the few known concepts that could move very large human spacecraft through the solar system at speeds far beyond chemical rockets. The scale of the idea is important. Orion was not imagined only as a small probe or a delicate laboratory vehicle. It was studied as a way to move heavy ships, possibly ships with crews, shielding, supplies, and large working spaces. That made it fundamentally different from high-efficiency electric propulsion, which can move small spacecraft with great economy but very little force. Nuclear pulse propulsion was not gentle in its source of energy, but the engineering goal was to turn those violent external pulses into controlled vehicle motion. Small-scale tests using conventional explosives helped show that a pusher plate system could survive repeated impulses in principle. The nuclear version was never flown, but the basic physics was not the reason the program ended. Project Orion ran from the late 1950s into the mid-1960s, with serious involvement from physicists and engineers including Ted Taylor and Freeman Dyson. It belonged to a period when nuclear technology was being considered for many roles that later became politically and environmentally unacceptable. The calculations were striking because nuclear energy changes the propulsion problem at its foundation. Chemical rockets release energy from molecular bonds. Nuclear devices release energy from the atomic nucleus, where the available energy per unit of mass is vastly larger. That higher energy can produce a much larger change in velocity without forcing the spacecraft to carry impossible amounts of chemical propellant. In mission terms, this means time changes. Mars is no longer a journey of many months. It becomes a journey that could be measured in weeks under some designs. Jupiter and its moons move from being nearly unreachable for crews with chemical propulsion to being possible expedition targets. Saturn becomes a destination that can be discussed in months, rather than as a remote robotic objective reached after long cruise phases. Even the outer planets and the Kuiper Belt begin to enter the range of human planning, not as easy places, but as places that a large, well-shielded, high-energy ship could reach within a career. This is the first propulsion tier that truly redraws the human solar system. Nuclear thermal propulsion improves the path to Mars. Nuclear pulse propulsion changes the meaning of distance between planets. It does not make the solar system small, but it reduces travel time enough that human health, mission duration, and emergency planning move into a different regime. A fast trip is not automatically safe, Yet many deep space risks grow with time. Radiation dose accumulates, mechanical systems age, food reserves are consumed, psychological strain develops. Every month removed from a long mission has value. By shortening the transit, nuclear pulse propulsion would reduce some of the most difficult burdens that chemical missions carry. It could also lift far heavier payloads onto deep space trajectories. That mass capacity is not a minor detail. For human exploration, mass can mean shielding, larger habitats, redundant systems, repair equipment, medical capability, and stored supplies. A propulsion system that can move large mass quickly does not merely make a ship faster, it makes the ship more survivable. It allows designers to stop treating every protective measure as a near impossible luxury. This is why Orion occupies such an unusual place in the history of spaceflight. It was extreme, but it answered real constraints rather than ignoring them. It recognized that deep space crews would need mass, and it proposed an engine powerful enough to move that mass. Still, the same feature that made Orion powerful also made it unacceptable. A system that depends on repeated nuclear detonations raises safety, environmental, legal, and political problems on a scale that cannot be treated as a detail. Launching such a vehicle from Earth would be especially problematic. A failure in the lower atmosphere could spread radioactive material. Even if assembled in orbit, the explosive units would have to be manufactured, transported, guarded, and handled with extraordinary security. The use of nuclear devices in space also carries military implications, because the boundary between propulsion hardware and weapon technology would be difficult for other nations to trust. These concerns were not irrational obstacles placed in the way of progress. They were part of the real cost of the concept. The Partial Test Ban Treaty of the early 1960s prohibited nuclear explosions in the atmosphere, in outer space, and underwater. The treaty helped reduce the environmental and political dangers of nuclear testing, and it made a nuclear pulse spacecraft effectively impossible under the legal order that followed. In that sense, Orion did not lose only to engineering difficulty. It lost to a broader decision about what kinds of nuclear activity humanity would allow. That distinction matters because it changes how the technology should be understood. Nuclear pulse propulsion is not like an engine that failed a ground test and disappeared because the physics would not cooperate. It is closer to a capability that entered conflict with law, risk, and global security. The result is an uncomfortable balance. The most capable near-term concept for opening the solar system to human crews is also one of the hardest to imagine using responsibly. There are possible ways to reduce some risks. A vehicle could be assembled far from Earth. It could use carefully designed pulse units intended for propulsion rather than weapons. It could operate only outside regions where fallout or blast effects threaten the planet. It could be placed under international control. Yet each solution introduces new problems of trust, verification, cost, and failure response. A nuclear pulse program would not be only a space program. It would be a geopolitical structure. It would require nations to agree that nuclear explosive technology in space can be separated from military escalation. That is a high requirement, and it may remain higher than the engineering requirement. Even if the vehicle could be built, permission to build it may be harder to obtain than the materials, calculations, or mechanical systems. The scientific promise of the destinations opened by such propulsion is substantial. Europa, with its hidden ocean beneath ice, becomes reachable by crews who could operate in the Jovian system rather than study it only through delayed signals. Callisto could serve as a safer base beyond the worst of Jupiter's radiation belts. Titan, with its thick nitrogen atmosphere and complex organic chemistry, could be studied directly by human teams rather than only by landers and orbiters. Enceladus, releasing material from its subsurface ocean into space, could become one of the most important biological targets beyond Earth. A nuclear pulse ship would not answer the question of life elsewhere by itself, but it could place human explorers near the worlds where that question is most concrete. It would turn the outer solar system from a sequence of robotic flybys and orbiters into a possible field of human investigation. That is the attraction. The destinations are not symbolic. They are scientifically rich places where the conditions for chemistry, oceans, energy, and habitability can be examined closely. The risk is that the vehicle able to reach them would be built around the same physical processes humanity has spent decades trying to control, limit, and keep away from conflict. This tension gives nuclear pulse propulsion a strange status. It is both practical and nearly unreachable. It is practical in the sense that its physics is known. Its core mechanism was analysed deeply, and its performance would be high enough to transform crewed travel. It is unreachable in the sense that modern law, public trust, launch safety, and arms control make it extremely difficult to revive. Future designs might avoid classic nuclear bombs and use pulsed fusion or other methods that preserve the advantage of repeated high-energy impulses without the same treaty burden. Those concepts remain less mature than Orion itself, but they point toward a possible compromise. The underlying lesson is clear. The solar system does not require magic to open. It requires energy, mass capacity, and the ability to shorten travel times. Nuclear pulse propulsion offers all three, but at a political and ethical price that may be too high. The Forbidden Engine shows that the limit on human travel is not always located in nature. Sometimes the physics permits a path, and the more difficult question is whether civilization can accept the path that physics has provided. Fusion changes the distance problem because it reaches into a deeper store of energy than fission or chemistry can provide. In a chemical rocket, energy comes from the rearrangement of electrons around atoms. In a fission system, energy comes from splitting heavy atomic nuclei. In fusion, light nuclei are forced together until they become heavier nuclei, and the difference in mass is released as energy. This is the process that powers the sun and every ordinary star. It is also the reason fusion has remained one of the most important long-term hopes for advanced propulsion. The energy density is high enough to make ordinary interplanetary distances feel different, but the process is difficult enough that it has not yet become an operating power system, let alone a flight engine. The promise and the obstacle sit very close together. Fusion fuel can be light, compact, and energetic, but it does not behave like ordinary propellant that can simply be burned in a chamber. Fusion requires temperature, pressure, and confinement conditions far beyond everyday materials. The fuel becomes plasma, an ionized gas where electrons and nuclei move separately. To make the nuclei fuse, the system must keep that plasma hot and dense long enough for reactions to occur faster than energy escapes. This is the central difficulty. Stars solve it with gravity, using enormous mass to hold their interiors together. A spacecraft cannot carry a star. It has to create controlled fusion through magnetic fields, laser compression, pulsed magnetic systems, or other methods that still remain difficult to engineer. The progress of fusion research has been real, but it has been slow because the task is not merely to start fusion. Small amounts of fusion can be produced in laboratories. The deeper challenge is to produce more usable energy than the whole system consumes, then repeat that process reliably, then make the equipment compact, durable, and light enough to matter for spaceflight. A ground power plant can be massive, a rocket engine cannot. A terrestrial reactor can rely on large buildings, maintenance crews, external power grids, and heavy shielding. A fusion spacecraft must carry its reactor, radiators, magnets, fuel, control systems, and protection through space while still leaving enough mass for the crew and mission. This makes propulsion harder than power generation. Even though propulsion is one of the most attractive uses of fusion, if the reaction products can be directed out of the vehicle as exhaust, the engine may convert nuclear energy into thrust more directly than a power plant converts heat into electricity. In the best case, a fusion rocket does not only produce electricity to run another engine, it uses the charged particles from the fusion reaction, or a heated propellant driven by fusion energy, to produce very high exhaust velocity. That is what changes the map. A fusion-driven spacecraft could, in advanced designs, reach exhaust speeds measured as a meaningful fraction of light speed. Even if the actual ship travels much slower than the exhaust, the available velocity change would be far beyond chemical or nuclear thermal systems. The result would be a solar system that no longer has the same practical shape. Mars could become a journey of days or weeks rather than months, depending on the design and acceleration profile. Jupiter could move into the range of ordinary crewed expedition planning. Saturn, Titan, and Enceladus could become reachable without committing a crew to the long, vulnerable coast phases that define present robotic missions. The Kuiper belt would still be distant, but not inaccessible in the old sense. The heliopause, where the sun's outward flowing solar wind gives way to interstellar space, could become a destination for human scientific missions rather than a boundary crossed only by aging probes after decades of travel. This would be a second redrawing of the map after nuclear pulse propulsion. Nuclear pulse opens the solar system by using repeated explosive energy. Fusion could open it in a cleaner and potentially more controllable way, if the engine can be built. The difference is not only speed. Fusion power could also support habitats, laboratories, manufacturing, thermal control, and high-power instruments far from the sun. Beyond Mars, solar energy becomes weaker. At Jupiter, it is greatly reduced, and at Saturn it is weaker still. A fusion spacecraft would carry its own strong energy source, making it less dependent on sunlight and more capable of operating in the outer system. This matters for human missions because power is survival. A crew far from Earth needs heat, light, air circulation, water recycling, communication, computing, medical systems, and possibly artificial gravity mechanisms or large electromagnetic shielding. Propulsion begins the journey, but power sustains it. Fusion may offer both. That combined role is why it remains so important even though practical fusion propulsion is not close. The most careful way to describe fusion's future is to separate possibility from schedule. The physics of fusion is known. Fusion happens in stars, in laboratory experiments, and in thermonuclear weapons. The remaining problem is controlled, useful, repeatable, economical fusion. Recent ignition experiments have shown that fusion fuel can produce more energy than the laser energy delivered directly into the target, but the entire facility still consumes much more energy than the reaction provides. Large magnetic confinement projects continue to pursue sustained burning plasma and power gain. Private companies are exploring compact magnet systems, pulsed approaches, field reverse configurations, and other designs. Some may fail. Some may become useful for power but not propulsion. Some may teach enough to shape the next generation of engines. The uncertainty is genuine, and any claim that fusion rockets are just around the corner would be too confident. But it would also be wrong to treat fusion as fantasy. It is a hard engineering frontier built on established nuclear physics. For human travel, the more important question is what level of performance fusion can eventually reach. A modest fusion engine might make Mars safer and the outer planets more realistic. A highly advanced fusion engine could push large ships to several % of light speed. That still sounds small beside the speed of light, but it is enormous compared with present spacecraft. At 1% of light speed, the nearest star remains a journey of more than 4 centuries. At a few percent, it becomes a journey measured in 1 or 2 centuries. This is not a single lifetime mission, but it moves interstellar travel from absurd timescales into the realm of generation ships or suspended animation concepts. The stars do not become nearby. They become numerically reachable in a way they are not for chemical rockets. That difference is profound. A civilization with fusion propulsion could send large robotic probes to nearby stars on timescales that matter to institutions rather than geological archives. It could send human generation vessels if the biological, ethical, and social problems were solved. It could establish a sustained presence throughout its own solar system, building industrial and scientific systems around the Moon, Mars, asteroids, outer planet moons, and distant reservoirs of ice and organics. The path to the stars would then grow out of a solar system civilization, not from a single heroic launch from Earth. This may be the most realistic role of fusion. It may not immediately produce fast starships. It may first create the infrastructure that makes any later starship possible. Large ships need fuel production, assembly yards, radiation shielding materials, closed ecological systems, repair capacity, trained crews, and long-term governance. Those are easier to develop across a working solar system than on one planet. Fusion propulsion could therefore expand human reach in stages. First, faster Mars missions, then reliable movement among the inner planets and asteroids, then crewed expeditions to Jupiter and Saturn, then bases or long-duration research platforms near moons with oceans, thick atmospheres, or complex chemistry, then missions to the heliopause and the inner Oort cloud. Only after that does interstellar travel become a continuation of experience rather than a leap into the unknown. This gradual path is less dramatic than a single jump to another star, but it is more coherent. Every stage teaches the next one. Every distant mission develops systems that later missions need. The same fusion reactor that powers an outer planet ship teaches engineers about heat rejection, maintenance, plasma control, fuel handling, and long-duration reliability. The same habitat that keeps a crew alive near Saturn teaches lessons for a ship crossing between stars. The same shielding that protects against solar and planetary radiation begins the work of protecting against galactic cosmic rays. Fusion does not remove the biological problem, the deceleration problem, or the social problem. It changes the scale on which those problems can be addressed. It gives civilization enough energy to attempt them seriously. That is why fusion sits at the center of the long-distance answer. It is not the final ceiling under known physics. Antimatter and beamed propulsion point toward higher velocities, but fusion is the first advanced tier that could plausibly combine large payloads, high energy, long-duration power, and a path from present research to future ships. If it succeeds, the human frontier would no longer be defined mainly by the distance from Earth to Mars. It would be defined by how far a fusion-powered society can build, maintain, and trust its systems. The stars would still be far beyond ordinary human scale, but the space between them would become a distance that engineering can begin to measure. Antimatter sits near the upper edge of rocket propulsion allowed by known physics. Because it uses energy in the most concentrated form, nature provides. Ordinary matter has mass, and antimatter has the same mass with opposite charge and related quantum properties. When a particle meets its antimatter counterpart, both are destroyed, and their mass becomes energy and other particles. In principle, no chemical fuel, no fission fuel, and no fusion fuel can match that conversion. A rocket able to direct even part of this energy into a useful exhaust could reach velocities far beyond any engine discussed so far. This is why antimatter appears so often in serious long-range studies. Despite being nowhere near practical use, it is not included because it is convenient. It is included because the energy density is high enough to make the nearest stars reachable on human timescales, at least in the mathematics. A ship travelling at 10% of light speed would reach Proxima Centauri in a little more than 40 years. At 20% of light speed, the same crossing falls to a little more than 20 years, before accounting for acceleration, deceleration, and the actual path through space. These are still long journeys, but they belong to a human lifetime rather than to deep history. The difference between a century-spanning generation vessel and a mission completed by the people who began it may depend on this kind of velocity. Antimatter is one of the few known energy sources that points towards such speeds without asking physics to change. Its difficulty is not conceptual. The difficulty is obtaining it, storing it, and using it without destroying the vehicle it is meant to move. The universe around Earth is made almost entirely of ordinary matter. Antimatter appears naturally in small amounts in high-energy processes, but not in the quantities required for propulsion. Human laboratories can produce antiparticles in accelerators, yet the amounts are extraordinarily small. Producing them requires enormous energy, and most of that energy does not become stored antimatter. It is lost into heat, radiation, secondary particles, and the inefficiencies of the accelerator system. Across all human history, the total manufactured antimatter is tiny, measured at scales far below what any spacecraft would need. A crude interstellar engine would not need a few trapped particles for study. It would need material measured in grams, perhaps kilograms, depending on design, efficiency, payload, and mission profile. That gap is not merely large. It is one of the largest gaps between a known physical principle and a usable technology in all of propulsion. The storage problem is just as severe. Antimatter cannot touch ordinary matter. A container wall is ordinary matter. Dust is ordinary matter. Residual gas inside a tank is ordinary matter. Any contact releases energy immediately. In laboratories, charged antimatter particles can be held in the electromagnetic traps, suspended away from contact with material walls. Neutral antimatter, such as antihydrogen, is much harder to confine because it does not respond in the same simple way to electric fields. A spacecraft would need a containment system that operates perfectly for years or decades, through launch vibrations, thermal changes, radiation, maneuvers, power fluctuations, and possible impacts. The consequences of failure would not be limited to losing propellant. The propellant itself would become an explosion. This makes antimatter unusual among fuels. Most dangerous propellants are dangerous because they burn, leak, poison, or detonate under certain conditions. Antimatter is dangerous because its normal interaction with the rest of the ship is annihilation. Even if production and storage improved greatly, the engine would still need to direct the released energy. Annihilation does not automatically produce a neat stream of exhaust. It can produce gamma rays, charged pions, neutrinos, and other particles depending on the reaction. Some of these are difficult to reflect, absorb, or channel. Neutrinos mostly escape without helping the spacecraft. Gamma radiation is deeply penetrating and creates shielding problems. Charged particles can in principle be guided by magnetic fields, which is why many antimatter propulsion ideas focus on reaction products that can be magnetically directed. But each conversion step reduces efficiency. Every part of the energy that cannot be turned into thrust becomes heat, radiation dose, or lost energy. The theoretical energy density remains extraordinary, but a real engine would be judged by what fraction of that energy becomes controlled motion. Antimatter therefore defines a ceiling more than it provides a plan. It shows what a nearly perfect rocket fuel might allow if civilization could manufacture and confine it at scale. It does not show a near path from present facilities to a starship. The other approach to very high speed removes the propellant problem by removing the engine from the spacecraft. A light sail is pushed by photons, the particles of light. Each photon carries momentum. When light reflects from a sail, it transfers a tiny push. For ordinary sunlight, that push is weak, though it can matter for small spacecraft over time. A laser-driven sail strengthens the effect by using a powerful beam aimed at a very light reflective surface. The energy source stays at home. The spacecraft does not carry fuel for acceleration. It carries the sail and the payload. This changes the rocket equation because the vehicle is no longer forced to accelerate its own propellant. For small payloads, the advantage is enormous. A gram-scale probe attached to an extremely thin sail could, in principle, be pushed to a significant fraction of light speed by a ground or space-based laser array. Concepts like Breakthrough Starshot have explored this path for robotic interstellar probes, especially toward the Alpha Centauri system. The numbers are striking because they show a way to send instruments to another star within decades rather than tens of thousands of years. The probe would not slow down easily, and the data return would be difficult, but the basic architecture avoids the impossible propellant masses that defeat chemical rockets. For robotic exploration, laser sails remain one of the most interesting known concepts. For human travel, the same idea runs into scale. A person cannot be reduced to grams. A crewed spacecraft requires a pressure vessel, water, food, shielding, medical systems, computers, power, and waste handling. It may need artificial gravity or large rotating structures. It needs redundancy because repair options are limited. Even a very minimal crewed interstellar ship would be many orders of magnitude more massive than a wafer-scale probe. To accelerate that mass to the same fraction of light speed, the laser power and optical system would have to expand by comparable orders of magnitude. The beam would have to remain focused across enormous distances as the sail recedes. The sail would have to stay aligned, stable, reflective, and cool under extreme illumination. Any absorbed fraction of the beam would become heat. For a thin sail, even small absorption can be destructive if the power is high enough. Materials would need to be light, strong, highly reflective, resistant to heating, and manufacturable at immense scale for a crude version. The laser array would itself be a major piece of civilization-level infrastructure, requiring power generation, beam control, adaptive optics, safety systems, and maintenance. A probe-scale version is hard. A human-scale version is far beyond known engineering. There is also the arrival problem. A laser sail accelerated from the solar system is pushed from behind while the beam remains effective. Once the beam can no longer maintain focus, the spacecraft coasts at the destination. Unless it carries another method of braking, it passes through the star system at high speed. A robotic flyby can still be valuable because instruments can gather data during the brief encounter. A human mission cannot be judged the same way. Spending decades in transit for a fast passage through another system, with no stopping and no return, would be a very limited form of exploration. Stopping would require an additional system, perhaps a magnetic sail, a photon sail braking against the destination star, onboard propulsion, or a pre-built laser array waiting in the target system. The last option requires prior infrastructure, which removes it from a first mission. This is why light sails and antimatter occupy different places in the distance question. Antimatter keeps the engine on the ship and offers extreme energy density, but demands a fuel that humanity cannot yet produce or store usefully. Laser sails keep the engine at home and may accelerate tiny probes to interstellar speeds. but they do not scale naturally to crewed vessels. One offers fuel without practicality. The other offers propulsion without mass. Both are important because they mark the edge of present imagination under known physics. They show that the nearest stars are not separated from humanity by a logical impossibility. They are separated by production, storage, materials, power, control, braking, shielding, and scale. For probes, the path may be shorter. For people, the path remains much longer. The calm conclusion is that no present technology can send humans to another star at the speeds needed for arrival within a lifetime. Antimatter describes what such propulsion may require in energy terms. Laser sails suggest how early robotic scouts might cross first. Together, they move the question away from fantasy and toward a stricter understanding. The stars can be reached by known physics, but not by shrinking the problem. They require either a fuel almost too difficult to handle or an external engine almost too large to build. The boundary is not the dream of speed. The boundary is the system needed to make speed survivable, directed, and useful. Arrival is not the same as reaching a place on a map. A spacecraft can cross the distance to another world and still fail the deeper mission if it arrives too fast to stay. This is one of the quietest problems in deep space travel, because acceleration receives most of the attention. Engines are usually described by how powerfully they can push a ship outward, how fast they can make the crossing, and how much distance they can remove from the schedule. Yet every serious crewed mission has a second half. The ship must give back the speed it gained. It must enter orbit, match motion with a planet or moon, or slow enough to begin operations in a star system. Without that step, the journey becomes a flyby. A flyby can be scientifically valuable for a probe, and even a crude flyby of a distant system would be remarkable, but it is not settlement, not landing, not sustained exploration. It is a brief passage through a region that took years, decades, or centuries to reach. The difference matters most at interstellar velocity. A ship crossing to Proxima Centauri at 10% of light speed is moving fast enough to traverse large portions of a planetary system in hours or days. Instruments might collect data during that passage, but the crew would not have the time or control needed to examine worlds carefully, alter course repeatedly, or place the vehicle into orbit. The ship would continue outward, carrying its passengers beyond the very destination that justified the mission. In that sense, a stopping is not a secondary convenience. It is what turns travel into arrival. The physics is straightforward. To slow down from a given speed requires a change in velocity comparable to the change that created that speed in the first place. If a spacecraft uses engines to accelerate to 10% of light speed, then uses the same kind of engines to slow at the destination, it needs roughly the same scale of propulsive effort again. The exact details depend on engine efficiency, trajectory, mass loss, and mission architecture, but the basic burden remains. Deceleration is not free. It asks for energy, propellant, time, hardware, and heat management. For a rocket that carries its own fuel, this creates a severe penalty. The propellant used for slowing down must be carried during the acceleration phase. That means the outbound burn must accelerate not only the crew habitat, structure, shielding, and supplies, but also the fuel reserved for arrival. The fuel for arrival then demands additional fuel for departure, and the rocket equation begins to tighten around the entire mission. A design that looks difficult when only acceleration is counted can become impractical once braking is included. This is one reason interstellar mission studies often separate flyby missions from rendezvous missions. A flyby avoids the main braking burden and can therefore be much lighter. A rendezvous mission has to pay the full price of being useful after it reaches the target. There are ways to avoid carrying all braking propellant from home, but each comes with its own difficulty. One option is to turn the spacecraft around during the journey and thrust in the opposite direction for the second part of the trip. This is conceptually clean. The same propulsion system that adds speed later removes it. The advantage is control. The crew does not depend on unknown conditions in the destination system. The engine provides the braking, and the navigation can be planned with precision. The cost is mass. Carrying the energy and propellant for both halves of the journey makes the initial vehicle much heavier. For chemical propulsion, this is impossible at interstellar speeds. For fusion or antimatter propulsion, it may become physically possible, but still enormously demanding. A second option is to use the environment as a brake. The space between stars contains thin plasma, mostly hydrogen and helium. A spacecraft could deploy a large magnetic field that interacts with charged particles in this medium. The field would act like an invisible sail, transferring momentum to the interstellar gas and slowing the vehicle gradually. This kind of magnetic braking has an important strength. It uses material already present along the path and does not require the ship to expend large amounts of propellant. It also has limits. The interstellar medium is thin, and its density varies. The braking force depends on speed, field strength, spacecraft mass, and local plasma conditions. A magnetic sail large enough to slow a crewed vessel may require superconducting loops, power systems, deployment structures, and protection against damage. It would have to operate reliably for long periods in deep space. If it brakes too slowly, the ship may enter the target system still moving too fast. If it is too large or too heavy, it adds to the mass that had to be accelerated at launch. The idea remains attractive because it uses the journey's environment rather than only onboard fuel, but it is not a solved system. A third option is to use light from the destination star. A reflective sail can be arranged so that photons from the star push against the incoming spacecraft. This is photon braking. It is elegant because it uses the star itself as the energy source. No propellant needs to be burned, and the braking can begin before the ship reaches the inner system. The weakness is that starlight is gentle compared with a powerful launch laser or a rocket engine. Around a bright sun-like star, the pressure can matter if the sail is large and the spacecraft is light. Around a dim red dwarf such as Proxima Centauri, the available radiation pressure is much smaller. A crewed spacecraft is also heavy, especially if it carries shielding and life support. The sail needed to slow such a ship would be vast, and it would have to survive deployment after decades of flight. It would also have to handle dust impacts, thermal stress, and precise orientation while moving at a significant fraction of light speed. Photon braking may help a small probe. It may assist an advanced mission. By itself, it is not an easy solution for a human starship. A fourth possibility uses the target star's stellar wind rather than its light. Stars release charged particles outward into space. A magnetic sail can interact with that flow as the spacecraft approaches, using the star's own wind to reduce speed. The effectiveness depends strongly on the star. A young active star may provide a stronger wind but also a harsher radiation environment. A quieter star may be safer but offer less braking force. Red dwarfs can flare intensely, complicating the environment near their habitable zones. A mission depending on stellar wind braking would need detailed knowledge of the target system before committing a crew. Robotic precursors would have to measure plasma density, magnetic activity, dust distribution, planetary positions, and radiation conditions. This points to a wider principle. Human interstellar travel cannot responsibly be the first close investigation of another system. Before a crew goes, machines must go first. They must map the braking environment as carefully as they map the planets. Deceleration also affects where humans would choose to go. The nearest star is not automatically the best destination if it is difficult to enter or operate within. A slightly farther system with a brighter star, calmer radiation environment, and confirmed planets may be a better target than a closer red dwarf with unstable conditions. The energy required to reach a star is only part of mission selection. The ability to slow down safely may decide whether the destination is practical. This becomes especially important when considering habitable planets. A world may orbit in the right temperature range, but if its star makes braking unreliable or its system contains dense dust hazards, the mission becomes more dangerous. In deep space planning, the best destination is not only the one that is nearest or most interesting, it is the one whose entire approach, arrival, and long-term operating environment can be managed. The braking problem also shows why infrastructure changes everything. A first mission to another star must carry or improvise its own way to stop. Later missions could arrive into a system where earlier robotic or automated missions have prepared assets. They might use fuel factories built from asteroids, beam stations assembled by machines, navigation beacons, or magnetic braking structures placed along the approach. This sounds far beyond present capability, but it follows a familiar pattern. The first crossing is the hardest because nothing waits at the far end. Once infrastructure exists, the route becomes less isolated. For the first human interstellar mission, that support would probably have to be delivered by machines long before any crew departed. Acceleration asks how to leave. Deceleration asks whether the mission can become a presence rather than a passage. The answer determines the meaning of the voyage. A civilization may send tiny laser-pushed probes on fast flybys long before it can send people who stop. It may send fusion-driven robotic craft that brake slowly using sails or magnetic fields. It may spend generations learning how to use the interstellar medium and stellar radiation as part of the propulsion system. Only after those methods mature does a crewed rendezvous mission begin to look responsible. The distance to another star is therefore not measured only in light years. It is measured in the ability to remove speed at the end of the crossing. Until that is solved, the nearest star remains a place that can be passed, not truly reached. Interstellar space is often described as empty, and compared with any environment near Earth, that description is reasonable. The density of matter between the stars is extremely low. There is no breathable air, no weather, no surface, no ocean, and no nearby source of warmth. A spacecraft moving slowly through such a region would meet very little material, but a spacecraft moving at a significant fraction of light speed experiences the same environment differently. At those velocities, even sparse matter becomes part of the engineering problem. The thin gas between stars is made mostly of hydrogen and helium, with traces of heavier atoms, plasma, molecules in denser clouds, and small dust grains spread unevenly through the galaxy. In the local interstellar neighborhood, the average density may be around 1 atom per cubic centimeter, though the real value changes from place to place. That sounds almost like nothing. For a fast ship, it is not nothing. Each atom strikes the leading surface with the speed of the spacecraft. At 10% of light speed, an incoming hydrogen atom carries far more energy than it would in ordinary spacecraft conditions. A single atom is not a visible threat. It is too small to punch a hole in a hull by itself. The problem is duration and accumulation. Over decades of travel, the ship sweeps through an enormous path. The leading surface receives a continuous stream of impacts. Those impacts can erode material, heat surfaces, alter coatings, and create secondary radiation. The faster the ship moves, the more severe the interaction becomes. A slow probe can pass through the interstellar medium as if through a near-perfect vacuum. A relativistic human spacecraft has to treat the same medium as a long, low, density particle beam. This is one reason speed cannot be considered only as a benefit. Higher velocity shortens travel time, reduces the number of years the crew spends in deep space, and makes nearby stars more reachable within human planning. But higher velocity also increases the energy of every collision with gas and dust. The mission trades time risk for impact risk. At modest speeds, the crossing may take too long for human systems. At higher speeds, the shielding problem becomes more severe. There is no simple point at which all constraints vanish. The ship must find a velocity where propulsion, radiation, impact protection, life support, and arrival all remain within possible limits. Dust is more dangerous than gas because a dust grain has much more mass than an atom. Interstellar dust includes tiny particles of carbon, silicates, ice, and complex compounds. Many grains are extremely small, far below what unaided eyes could see, but at a tenth of light speed their energy becomes serious. A grain with the mass of a microscopic speck can strike with the force of an explosive impact on the scale of the local structure it hits. Larger grains are rarer, but a single unexpected collision could damage a sail, sensor, radiator, shield, or exposed structural element. A crewed spacecraft cannot depend on luck across light years. It would need a forward shield designed for a range of particle sizes, including particles that instruments might never detect in advance. The shield could be made from layered materials, sacrificial ice, water, graphite, metal foams, or electromagnetic systems that deflect charged particles before they touch the hull. Each option adds mass or complexity. A thick physical shield protects better, but makes the ship harder to accelerate. A magnetic shield may reduce charged particle exposure, but will not stop neutral dust grains. A cloud of small particles released ahead of the ship might break incoming grains into plasma before they reach the main hull, but that system must be replenished and controlled. No single method is enough for all threats. A real interstellar spacecraft would likely use several layers, each meant to reduce the burden on the next. The leading shield would be one of the most important parts of the whole vehicle, because it is the first structure to meet the galaxy at speed. Radiation adds another layer of difficulty. Galactic cosmic rays are high-energy particles moving through space from sources such as supernova remnants and other energetic astrophysical environments. They are present in the solar system, but the sun's magnetic influence reduces some of their flux inside the heliosphere. Beyond the heliopause, that partial protection is gone. A crewed interstellar spacecraft would remain immersed in galactic cosmic radiation for the full crossing. These particles can pass through spacecraft walls and human tissue, ionizing atoms along their paths and damaging biological molecules. Shielding against the most energetic particles is difficult because dense shielding can produce secondary radiation when struck. A high-energy particle hitting the hull may generate a shower of other particles, including neutrons and gamma rays, which can penetrate deeper into the spacecraft. This means shielding cannot be designed by simply adding more metal. In some cases, heavy material can make the internal radiation environment worse. Hydrogen-rich materials such as water or certain plastics are often better for many particle types, and water has the additional advantage of being useful for life support. A starship might wrap crew compartments in water tanks, food stores, or fuel reserves to combine protection with necessary mass. Even then, decades of exposure remain a major medical concern. The radiation problem does not stand apart from the impact problem. When a fast ship strikes interstellar atoms, the interaction itself can create radiation. From the spacecraft's frame of reference, the gas ahead is arriving as a high-energy stream. Protons striking the forward shield can generate secondary particles. Dust impacts can produce plasma and bursts of energetic fragments. The front of the ship becomes not only a shield but a radiation source that has to be managed. Designers would need to place crew areas behind layered protection, separate sensitive electronics from direct exposure, and choose materials that reduce harmful secondary products. They would also need to protect external systems that cannot be hidden completely inside the hull. Radiators, antennas, sensors, sail structures, magnetic loops, and docking systems may all need some exposure to space in order to function. Each exposed component becomes vulnerable. The spacecraft cannot simply become a sealed ball of shielding, because it must reject heat, observe its surroundings, communicate, navigate, and possibly deploy braking systems at the destination. Heat is often overlooked, but it becomes more important as protective systems grow. A crewed ship produces waste heat from life support, computers, power systems, reactors, engines, and human activity. In space, heat can leave mainly by radiation, which requires radiators. Radiators need surface area, and surface area can be vulnerable to dust and radiation damage. A fast interstellar ship may have to hide radiators behind shielding during the highest risk phases, or design them with redundancy and self-repair. If fusion or antimatter power is used, heat rejection becomes an even larger engineering demand. The engine may produce energy at a scale that makes propulsion possible, but unused energy must go somewhere. A ship that cannot shed heat cannot keep its crew alive or its system stable. This connects the interstellar medium to the power system, the hull shape, and the mission profile. The vehicle's design is not only about moving quickly, it is about surviving the consequences of moving quickly through an imperfect vacuum. Navigation also changes over interstellar distance. The ship must know where it is, where the target star will be when it arrives, and how to adjust for small errors accumulated over years. Stars move, planets orbit. Dust clouds and plasma conditions may not be mapped with enough detail before departure. A tiny error in velocity or direction early in the mission can grow into a large miss after several light years. Autonomous navigation would therefore be essential. Communication with Earth becomes delayed by years, so the spacecraft cannot depend on real-time correction from home. It must identify stars, measure its motion, track its own systems, detect hazards, and make course decisions with high reliability. This is especially important if the ship intends to break into a target system. Missing the correct approach corridor may mean losing the chance to slow down efficiently. The interstellar medium is not an enemy in the ordinary sense. It is simply the material between stars, following the same physical laws as everything else. Its danger appears because human missions would cross it at speeds and durations far beyond current experience. Empty space becomes a cumulative environment. Gas becomes erosion and secondary radiation. Dust becomes impact hazard. Cosmic rays become a long medical exposure. Heat rejection becomes a structural problem. Navigation becomes a matter of autonomy across years of delay. None of these barriers violates physics, but each one makes the vehicle heavier, more complex, and harder to accelerate. That is the pattern of deep space travel. Solving propulsion reveals the next constraint rather than ending the difficulty. A ship fast enough to reach another star must also be strong enough to meet the matter between stars, quiet enough inside to preserve life, intelligent enough to navigate without immediate help, and protected enough that the crossing does not slowly destroy the people and systems it carries. Interstellar space is not a blank distance waiting to be crossed. It is a physical environment, thin but active, and any human journey through it would have to be designed around that fact from the first line of the mission plan. The human body is the most complex payload any spacecraft can carry. It is not passive mass, and it is not interchangeable with instruments or cargo. It is a living system shaped by Earth, by gravity, by air pressure, by a magnetic field, by a regular cycle of light and dark, and by a radiation environment softened by atmosphere. Space removes those supports one by one. A crewed ship can replace some of them with engineering. It can hold air at the right pressure, control temperature, recycle water, remove carbon dioxide, and provide light on a schedule. It can store food or grow part of it. It can monitor health and carry medical equipment. But the body still knows, at a physical level, that it has left the conditions under which it evolved. This is why biology becomes a frontier equal to propulsion. A faster engine can reduce the length of a journey, but it cannot by itself make human tissue adapted to deep space. The first clear problem is weightlessness on Earth. Muscles and bones constantly work against gravity, even during quiet standing and movement, in orbit or during a long coast through space. That loading disappears. Bone tissue begins to lose mineral density because the skeleton is no longer carrying normal weight. Muscles weaken because they're no longer used in the same way. The heart and blood vessels adapt to fluid shifts as blood and other fluids move toward the upper body. Pressure changes around the head can affect vision and may alter how the brain and eyes respond over time. The immune system changes in ways that are still being studied. Sleep can be disturbed. Balance systems that depend on gravity signals become confused. Exercise helps. And modern space stations use resistance machines, treadmills, cycling devices, and careful schedules to reduce the damage. But reduction is not elimination. Months in weightlessness are already medically demanding. Years or decades would move beyond the evidence gathered so far. Artificial gravity is one possible answer, but it is not simple. A spacecraft could rotate, creating an outward effect that mimics gravity along the inside of a ring or tethered habitat. The principle is known. The challenge is building a rotating system large enough to be comfortable, stable, safe, and compatible with propulsion, docking, radiation shielding, and internal operations. A small rotating habitat can create uncomfortable motion effects because the head and feet experience noticeably different acceleration, and because turning the head inside such a space can produce disorienting signals. A larger radius improves comfort but adds structure and mass. Artificial gravity may become essential for long voyages, yet it must be paid for with engineering complexity. The second major problem is radiation. Near Earth, the magnetosphere and atmosphere reduce much of the danger. On the way to Mars, and even more beyond the heliopause, crews face solar particle events and galactic cosmic rays. Solar particle events can deliver intense bursts of radiation during storms on the Sun. Galactic cosmic rays are more continuous and often more energetic, arriving from outside the solar system. They can pass through shielding and body tissue, ionizing molecules along the way. In cells, that damage can affect deoxyribonucleic acid, proteins, membranes, and other structures. The body repairs some damage constantly, but long exposure raises the chance that repairs fail or produce harmful changes. Cancer risk is the most discussed concern, but radiation can also affect the nervous system, the cardiovascular system, and the immune system. Shielding is possible, but it is heavy. Water, hydrogen-rich plastics, food stores, and fuel can be arranged around crew quarters to absorb some particles. A storm shelter can protect against solar events by concentrating shielding around a smaller space. The hardest galactic cosmic rays remain difficult because dense shielding can create secondary radiation when struck. A deep spaceship must therefore protect without simply becoming an impossible block of mass. The third problem is closure. Earth's biosphere is large, forgiving, and self-repairing over broad scales. A spacecraft is small and must recycle what it can. Air must be cleaned and renewed. Water must be recovered from humidity. Urine, washing, and waste streams. Food must be stored, grown, or produced from onboard systems. Microbes must be monitored because a closed habitat can allow unwanted biological changes to build up. Materials must resist mold, corrosion, wear, and contamination. A long mission cannot rely on constant resupply. The life support system must function more like a small managed ecology than a machine that can be replaced when parts fail. The difficulty rises sharply with duration. A Mars transit can carry large stores and rely on planned maintenance. A journey lasting many years requires deeper recycling and more autonomy. A generation ship would require something closer to a stable artificial environment where plants, microbes, water chemistry, air chemistry, human waste, and food production are managed across lifetimes. That is not only engineering, it is ecology under strict limits. Any imbalance must be corrected before it spreads. The fourth problem is medicine without rescue. In low Earth orbit, return is difficult but possible. On the way to Mars, evacuation is usually not available. Between stars, it is meaningless. A crew must handle injury, infection, pregnancy if allowed by mission design, dental emergencies, surgery, mental health crises, and chronic disease with the people and equipment on board. Medical systems would need diagnostic tools, stored drugs, sterile capability, robotic assistance, tissue repair methods, and perhaps biomanufacturing to produce medicines as needed. The crew would also need enough training to use them. A distant ship cannot assume that Earth will solve its emergencies. Communication delay makes real-time medical advice impossible. By the midpoint of an interstellar mission, a message to Earth, and the reply may take years. This creates a form of independence deeper than any previous expedition. The ship becomes its own medical, legal, and social world. The fifth problem is psychological continuity. Human beings can endure isolation, but the scale matters. Spacecraft are confined environments with limited privacy, repeated routines, dependence on others, and no natural landscape. Missions in polar stations, submarines, and orbital platforms show that mood, sleep, group cohesion, and motivation can shift over time. A voyage of decades changes the question. A crew cannot simply wait for the mission to end in the near future. The mission becomes life itself. Relationships form, weaken, and change. Authority structures age. Conflicts may not be avoidable by separation. Personal identity may become tied to a vessel moving through interstellar space with no immediate outside community. A well-designed habitat would need space not only for survival, but for ordinary human variation, quiet, work, recreation, ritual, education, conflict resolution, and grief. These are not soft details. They are operating requirements for any mission long enough to contain real human lives. Several proposed solutions try to reduce the biological burden by changing the condition of the crew during travel. Suspended animation is one of them. In medicine, cooling the body can slow metabolism for limited periods, and some animals can enter states of dormancy or survive extreme drying and later revive. These facts show that metabolism can be altered, but they do not mean humans can be placed safely into decades of sleep. Mammalian organs require oxygen, waste removal, temperature control, immune function, and repair. Brain tissue is especially sensitive. Preventing damage over long periods would require control at the cellular level that does not yet exist. If such a method were developed, it could change interstellar mission design profoundly. Food use would drop, psychological strain would lessen, aging might slow, a single crew could cross distances that otherwise require generations. But at present, long-term human suspended animation remains an open biological possibility. not a technology. Another path is adaptation rather than suspension. The body that leaves for the stars may not be biologically identical to the body that first reached orbit. Genetic medicine, cell therapy, and molecular repair are advancing fields on Earth. Future space travelers might receive treatments that improve radiation repair, reduce bone loss, protect the nervous system, or make tissues more resilient during low gravity. Some organisms tolerate radiation far better than humans because their repair systems are unusually effective. Studying those systems may eventually suggest ways to improve human resistance, though transferring such traits into a whole person safely would be difficult. Biology is interconnected. A change that protects one system may disturb another. Space adaptation would therefore require caution, ethics, and many stages of testing. The deeper point is that human limits are not entirely fixed. The species that began spaceflight with short orbital missions may become capable of longer journeys through medicine, habitat design, artificial gravity, and careful biological support. This possibility complicates the word human. If future travelers rely on altered cells, enhanced repair, artificial organs, long dormancy, or reproduction inside closed habitats, they remain part of humanity, but not in the simple form that first left Earth. Deep space may require a wider definition of human presence. The limit is not only how far present bodies can be carried, it is how far human life, with its memory, intelligence, culture, and continuity, can be protected while changing enough to survive. Propulsion may decide whether a destination can be reached in decades or centuries. Biology decides whether anyone can remain alive, sane, healthy, and socially whole along the way. Until that is solved, even the most capable engine still carries an unresolved biological problem at the center of the mission. A destination matters only when it changes the meaning of the journey. Distance by itself is not enough. A spacecraft can travel far and learn little if the target is poorly chosen, while a shorter journey can alter entire fields of science if it reaches the right place. This is why the question of human deep space travel eventually becomes a question of purpose. Mars is the nearest large step because it is a planet with a surface, resources, seasons, geology, ancient water records, and enough gravity to matter. But beyond Mars, the solar system contains places that may be more important scientifically than Mars itself. They are harder to reach, colder, farther from sunlight, and often more dangerous. Yet they hold some of the clearest tests of whether life is a local accident or a common outcome of planetary chemistry. Europa is one of those targets. It is a moon of Jupiter, covered by an ice shell and shaped by the gravity of a giant planet. Beneath its surface lies a global ocean. Inferred from magnetic measurements, surface geology, and the behavior expected from tidal heating. The ocean is not warmed mainly by the sun. Jupiter's gravity flexes Europa as it orbits, and that repeated flexing produces heat inside the moon. A world that should be frozen solid instead keeps liquid water hidden beneath ice. For astrobiology, that combination is important because liquid water, chemical energy, and long duration are the basic conditions that make life plausible. Europa does not prove that life exists beyond Earth. It proves that a major environment where life could be investigated exists within reach of advanced solar system travel. A crewed mission to Europa would not be simple. Jupiter's radiation belts are severe. The surface is cold, the ice is thick, and any landing system would need to avoid contamination while protecting the crew and instruments. Yet the scientific value is unusually high. Human teams operating near Europa could respond to unexpected data, adjust sampling plans, repair equipment, and coordinate orbiters, landers, ice-penetrating probes, and plume detectors in ways that delayed remote control cannot match. The purpose of going would not be symbolic presence. It would be direct investigation of an ocean world. Enceladus may be an even cleaner target in one respect, because it brings material from its ocean into space. This small moon of Saturn releases geysers from fractures near its south polar region. The Cassini spacecraft flew through those plumes and detected water vapor, ice grains, salts, organic compounds, and molecular hydrogen. That last ingredient matters because it can point toward reactions between water and rock, similar in broad chemical role to hydrothermal systems on Earth's seafloor. On Earth, such environments support ecosystems without sunlight. Enceladus therefore offers a rare advantage. A spacecraft may be able to sample a subsurface ocean without drilling through kilometers of ice. For human exploration, that changes the mission architecture. Scientists could place instruments in orbit, fly repeatedly through plume material, collect samples, analyze complex chemistry nearby, and decide quickly which signals deserve follow-up. The Moon is far from the Sun and deep within Saturn's system, so it requires propulsion, power, and radiation planning far beyond present crewed capability. But if fusion or another high-energy propulsion system made Saturn reachable on reasonable timescales, Enceladus would become one of the strongest arguments for sending people so far. It is not because the Moon is large. It is because its interior is accessible in a way few ocean worlds are. Titan offers a different reason to cross the distance. It is not mainly an ocean world in the same sense, although it may hide water below. Its surface is shaped by methane and ethane under a thick nitrogen atmosphere. Rivers, lakes, clouds, dunes, and organic chemistry exist there under temperatures far below anything on Earth's surface. Titan is chemically rich and physically strange, but it is not hostile in the same way as vacuum. Its atmospheric pressure is greater than Earth's at sea level, which means a person would not need a pressure suit in the ordinary sense, though breathing support and extreme cold protection would be essential. For scientists, Titan is a natural laboratory for complex carbon chemistry. It may preserve kinds of prebiotic processes that are difficult to study on modern Earth, where life has altered almost every environment. A human presence there would not be easy, but the thick atmosphere assists flight, slows descent, and provides local materials that future industry might use. Titan could become a place where exploration, chemistry, atmospheric science, and resource use overlap. It is also a reminder that habitability is not one simple category. A world can be unlivable for humans and still deeply important for understanding how organic complexity develops. The outer solar system contains other targets worth naming. Ganymede is the largest moon in the solar system and has its own magnetic field. Callisto orbits far enough from Jupiter's strongest radiation belts that it has sometimes been considered a more practical base for operations in the Jovian system. The small bodies of the Kuiper belt preserve cold records from the early solar system. The heliopause marks the transition into interstellar space and gives scientists a place to study how the sun's influence meets the galaxy. These destinations are not backup choices if the stars remain too difficult. They're part of the main story. A civilization able to explore them directly would already have become a deep space civilization. It would have learned how to operate far from sunlight, how to protect crews for long durations, how to build nuclear or fusion-powered systems, how to manage closed habitats, and how to send people to places where Earth is no longer the central practical reference. That experience would be the foundation for any later attempt to reach another star. Interstellar targets require a harsher form of selection. The nearer stars are not automatically the best places to send people, because nearness does not guarantee safety, useful planets, or scientific value. Proxima Centauri is the closest known star beyond the Sun, a red dwarf with at least one Earth-mass planet reported in its habitable zone. Its distance makes it the obvious first interstellar reference point, yet Proxima is an active star, and planets close enough to receive moderate warmth from a red dwarf may face strong flares, tidal locking, atmospheric loss, and difficult radiation conditions. A mission to Proxima would therefore require robotic precursors long before any crew departed. The first question would not be how inspiring the destination appears from Earth. It would be whether the planet has an atmosphere, whether its surface or terminator regions could support stable conditions, whether radiation makes close operations dangerous, and whether there is anything there that justifies the crossing. Alpha Centauri A and B offer a different kind of interest. They are Sun-like and slightly cooler stars in a nearby binary system, and their distance is only slightly greater than Proxima's. Stable planetary orbits are possible in parts of the system, but the full planet inventory remains uncertain. If a rocky planet in a temperate orbit were confirmed around either star, the scientific case would become much stronger. A Sun-like nearby target with a stable planet would be a more natural destination for human follow-up than a flare-active red dwarf, even if it were slightly harder to reach. Farther out, systems such as Tau Ceti become interesting because they are more similar to the Sun and may host multiple planets. Though distance quickly changes mission design, a journey of a few light years is already severe. A journey of 12 light years at a modest fraction of light speed may require generations, unless propulsion reaches far beyond fusion. This is why telescopes matter before starships. Direct imaging and atmospheric spectroscopy of nearby rocky planets could tell civilization where the real targets are. Oxygen, methane, water vapor, carbon dioxide, ozone, and other molecules in an exoplanet atmosphere would not automatically prove life. But certain combinations could make the question much harder to ignore. A confirmed biosignature within 20 light years would change the meaning of interstellar travel. The goal would no longer be simply to reach another star. It would be to examine a living or possibly living world closely enough to understand whether biology has begun there independently. That is the kind of purpose that can justify long planning, high risk, and enormous investment. Without such a target, robotic exploration may remain the responsible path for a long time. With such a target, the argument for eventual human travel becomes more concrete. The destinations worth crossing for are therefore not chosen by distance alone. They are chosen by what they can answer. Europa and Enceladus ask whether ocean worlds can host life. Titan asks how far organic chemistry can go in a cold, complex environment. The heliopause asks how a star meets interstellar space. Proxima asks whether the nearest planet beyond the Sun is truly a world or only a warning about red dwarf habitability. Alpha Centauri asks whether a nearby Sun-like system may contain a stable place for future exploration. These targets give the distance question its direction. Humans could travel farther simply to place a footprint somewhere remote, but the more durable reason to go is to reach environments where the evidence changes what is known. In that sense, the best destinations are not always the farthest. They are the places where travel becomes understanding. The real ceiling on human travel is not a single distance. It is a set of boundaries that move outward when one constraint is solved and stop again when the next constraint becomes dominant. The first boundary is historical and practical. Human beings have reached the moon, about 250,000 miles away, and have not yet gone farther. That record is not small, but it is close to Earth compared with every other destination that matters. The next boundary is Mars, which at favourable alignment can be about 34 million miles away. With chemical propulsion, Mars is difficult but plausible. It requires long transit times, careful radiation planning, reliable life support, surface systems, return architecture, and a level of institutional steadiness that has not yet been demonstrated for a crewed interplanetary mission. Still, Mars belongs to the same broad technological age as present spaceflight. It does not require antimatter, fusion, or new physics. It requires current methods pushed to their most disciplined form, with enough improvements to make the risk acceptable. Under the limits of chemical propulsion, Mars is therefore the practical near-term ceiling for a complete human mission. The Moon has been done. Mars is the door still waiting to be crossed. Beyond Mars, the answer changes only if propulsion changes. Nuclear thermal propulsion raises the quality of the Mars mission more than it changes the destination list. By heating hydrogen with a reactor, rather than relying on chemical combustion, it can shorten transit times and widen mission options. That matters because time in deep space is harmful. A shorter journey means less radiation exposure, less microgravity damage, fewer consumables, and more flexibility. But nuclear thermal propulsion does not make the outer solar system easy. It improves the inner solar system. It helps transform Mars from a fragile expedition into a more repeatable target. It may also become a bridge into routine nuclear operations beyond Earth, and that experience would matter for everything that follows. The next real expansion comes from propulsion with much higher energy. Nuclear pulse propulsion, if it were politically and legally possible, could open the solar system in a way chemical and nuclear thermal engines cannot. Its force comes from nuclear events delivered in pulses, and its advantage is the ability to move large spacecraft quickly. With such a system, Jupiter's moons, Saturn's moons, the Kuiper Belt, and perhaps the heliopause become reachable within human planning timescales. This is not because those places are safe or easy. Europa still lies inside a dangerous radiation environment. Enceladus is distant and cold. Titan is chemically rich but deeply alien to human biology. The outer system remains hard, but with enough speed and payload capacity, it stops being mostly a robotic domain and becomes a possible human domain. This is the solar system ceiling. It is not prevented by the known laws of nature. It is restrained by risk, treaties, nuclear politics, and the difficulty of building a system that civilization can trust. That distinction is important. Some ceilings are physical. Some are chosen because the cost of crossing them may be unacceptable. Fusion moves the boundary in a different way. If controlled fusion becomes a practical propulsion and power source, the whole solar system becomes more accessible, and the edge of interstellar travel begins to appear. Fusion could provide high exhaust velocity, long duration power, and the ability to support large ships far from the Sun. It could make the outer planets regular expedition targets and turn the heliopause into a reachable scientific boundary rather than a distant marker crossed only by long-lived probes. More advanced fusion could push spacecraft to a small but meaningful fraction of light speed. At that point, the nearest stars become possible for generation ships, long-duration robotic missions, or perhaps crews using biological methods not yet available. Fusion does not make interstellar travel easy. It does not solve radiation, dust, closed ecology, psychology, deceleration, or governance. But it changes the stars from unreachable by arithmetic into reachable by a civilization willing to build across centuries. This is a major difference. A journey of many tens of thousands of years is effectively outside human mission planning. A journey of 1 or 2 centuries is still severe, but it can be imagined as an institutional and biological problem rather than a meaningless drift. Antimatter marks the upper edge of known rocket energy. If it could be produced in large quantities, stored safely, and directed efficiently into thrust, it could make the nearest stars reachable within a human lifetime. That is its importance. It is not close to practical use. And it should not be described as an approaching technology. The production gap is enormous. The storage problem is severe. The radiation and engine design problems remain difficult, but antimatter shows where known physics points when the goal is a fast-crewed crossing to another star. It suggests that the nearest stellar systems are not forbidden. They are locked behind energy handling on a scale humanity has not begun to master. Laser-pushed sails offer a different route for small probes, because the energy source can remain in the home system. They may one day send robotic scouts toward Proxima Centauri or Alpha Centauri at a significant fraction of light speed. Those scouts could return knowledge that decides whether a later human mission has a target worth the cost. But light sails do not naturally scale to crewed ships. A person requires mass, and mass changes everything. The first interstellar travelers, if they ever go, will probably follow robotic precursors that have already mapped planets, dust, radiation, stellar activity, and braking options. No responsible civilization would send people blind into another star system when machines can reduce the uncertainty first. The hardest boundary that does not move is the speed of light. Nothing with mass can reach it under known physics. As a spacecraft approaches light speed, the energy needed for further acceleration rises without limit. This does not matter much for Mars or Jupiter, but it defines the scale of the galaxy. Even a ship travelling at 1/10 or 1/5 of light speed is slow compared with the Milky Way. Nearby stars become possible. The galaxy does not become a single human destination. It becomes a landscape for civilizations, not individuals. To cross large portions of it would require expansion over many thousands or millions of years, with settlements or self-sustaining communities moving outward step by step. Human travel at that scale is no longer a mission in the ordinary sense. It is history unfolding through space. The difference between a crewed expedition, a generation ship, and a spreading civilization becomes essential. A crew can reach Mars. A more advanced crew may reach the outer solar system. A generation ship may reach a nearby star. A civilization may spread farther if it survives long enough and keeps choosing to do so. The final answer is therefore layered. With present and near-present technology, humans can realistically aim for Mars. With nuclear thermal propulsion, that journey becomes faster and safer, but not fundamentally interstellar. With nuclear pulse propulsion, the solar system opens in principle, though politics and safety stand in the way. With fusion, the solar system becomes a working domain, and the nearest stars become long-term possibilities. With antimatter or some equally dense energy source, the closest stars may become reachable within a lifetime, provided biology and braking are also solved. Beyond that lies the steady wall of light speed and the enormous scale of the galaxy. The farthest humans could really travel is not set only by engines. It is set by the slow agreement between physics, biology, engineering, and purpose. Mars is the near answer. The outer solar system is the reachable frontier if civilization accepts the cost. The nearest stars are the long ceiling under known physics. Farther than that, the question stops being about a single crew and becomes about whether humanity can become a lasting patient presence across cosmic time. The universe allows more than current technology can reach, but it does not make any part of that reach effortless. Every added distance asks for a deeper form of endurance. The distance question settles into a quieter shape once every layer has been placed beside the others. Human travel into deep space is not stopped by one obstacle alone. It is slowed by many limits working together: the energy inside propellant, the mass of protection, the weakness of biology outside Earth, the difficulty of slowing down, the need for reliable closed habitats, and the patience required to build missions whose rewards may arrive long after the first decision is made. Yet none of that makes the outward path meaningless. It makes it clearer. The moon remains the first marker, close in cosmic terms but enormous in human history. Mars waits as the next complete test of whether people can live and work beyond Earth for long periods. The outer planets wait behind stronger propulsion and deeper endurance. The nearest stars wait behind a much greater threshold, where engines, bodies, and civilizations must all become more capable than they are now. The calm answer is not that humans are trapped forever near Earth, and not that the galaxy is ready to open. The answer lies between those extremes. Known physics allows a larger future than present technology can reach, but every step outward must be earned by solving real problems rather than by ignoring them. That may be the most honest form of wonder in the subject. Space does not become smaller when it is understood. Its scale becomes more precise. The path into it becomes more demanding, but also more real. And in that real path, measured by engines, shielding, time, and careful purpose, the human frontier remains unfinished, not because it is easy to extend, but because it has not yet reached the deepest limits of what nature permits.